Welcome back to Math 1324. We are in Chapter 8, Probability, and today we're going to talk about conditional probability, intersection, and independence. So in the previous section, we examined the probability of the union of two events and found that the probability of the union is related to the sum of the probabilities of the individual events using the following theorem. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. In this section, we learned that the probability of the intersection of the two events is related to the product of the individual probabilities. This result requires some background study of the concept of what's called conditional probability. So let's talk about conditional probability. The probability of an event might change if we are told of the occurrence of another event. So a couple of examples. The probability of drawing a heart from a standard deck of cards changes if we are told that the card drawn is a red card. Another example, if an adult 21 years or older is selected at random from all the adults in the U.S., the probability of that person having lung cancer would not be high. However, if we are told that that person was also a heavy smoker, the probability of that person having lung cancer would have to be revised and it would be a higher value. So we're going to use the notation, the probability of A given B. So did you hear how I read that? The probability of A given B to indicate the probability that an event A occurs when we know that the event B did occur. This type of probability is called conditional probability. And that little vertical bar, you say given. The probability of A given B. In the preceding examples, to set it up, in the card example, if A is the event that the card drawn is a heart, and B is the event the card drawn is red, we're going to consider the probability of A given B. In the second example, the events would be the event E, the adult has lung cancer, and the event F is the adult is a heavy smoker. The probability of E given F is the probability that the person selected has lung cancer, given that the person is a heavy smoker. Okay, so let's go start computing some of these things. What is the probability of rolling a prime number in a single roll of a fair die? So our sample space is going to be S equals the numbers 1 through 6. The event of rolling a prime number, we're going to let that event be A, and the prime numbers are 2, 3, and 5. So we're asking, what is the probability of event A? What's the probability of rolling a prime number? So the probability of event A is equal to the number of outcomes, in A over the number of outcomes in the sample space, which is 3 out of 6. So the probability of event A is 3/6. You can write that as 1/2 if you want to. Now suppose we want to know the probability of rolling a prime number in a single row of a fair die when we know that an odd number turned up. Okay, so we've got our sample space 1 through 6. Event A is that a prime number was rolled. Event B is that an odd number was rolled. Okay, so what's the new sample space going to be? The new sample space is going to be that it was an odd number. That's what it was given, okay? So the new sample space is B, 1, 3, and 5. All right, so we're wanting to know the probability of A given B. It's going to be the number of things in A intersect B over the number of things in B. Because your new sample space is B. There's 3 things in there. Now, which ones are in both A and B? You've got 3 and you've got 5. So there's 2 events in both A and B. The probability of A rolling a prime, given that you rolled an odd number, is going to be 2/3. So here's our formal definition of conditional probability. For events A and B in an arbitrary sample space S, we define the conditional probability of A given B by, right here, the probability of A given B is equal to the probability of A and B divided by the probability of B, provided the probability of B is not 0. Otherwise, you would be dividing by 0, and you can't do that. So we have to know that there's elements, there's outcomes in event B. Now, why is this true? I'm going to go over to the side and show you. The probability of A given B would be the number of outcomes in A and B over the number of outcomes in the sample space S, right? Now, the probability of B, so that's what this is. I just wrote that down. The probability of B is the number of items in B over the number of items in the sample space. Well, look, those would cancel. That's why you end up with the number of items in A and B over the number of items in just B. Okay? All right. Let's go do another example. Example number 4. A pointer is spun once on a circular spinner. So go see this figure over here. You're going to spin that pointer. The probability assigned to the pointer landing on a given integer between 1 and 6 is the ratio of the area corresponding to a circular sector of the whole circle. Okay, the probabilities of these events are given in the table. First thing we want to ask is this an acceptable probability assignment? Are each of these numbers between 0 and 1 inclusive? And the answer is yes. Now the second condition that must be met, do all those probabilities add up to 1? 0.1 plus 0.2 is 0.3, plus 0.1 is 0.4, plus 0.1 is 0.5, plus 0.3 is 0.8, plus 0.2 is 1. So yes, that is an acceptable probability assignment. So the first question, what is the probability of the pointer landing on a prime number? Let's let event E be that it's a prime number. So prime is 2, 3, and 5. Oops. Okay, so the probability of event E would be 0.2 plus 0.1 plus 0.3, which is 0.6. Second part of that question, what is the probability of the pointer landing on a prime number given that it landed on an odd number? So let's let F be the event that it landed on an odd number, which is 1, 3, and 5. So this question asks, what's the probability of it landing on a prime, probability of a prime, given that it was odd? Oops, not G, F. Okay, by our formula, that's the probability of E and F over the probability of F. Okay, what's the probability of F? Probability of F would be 1, 3, and 5. So you have 0.1, 0.1, 0.3. Would be 0.1 plus 0.1 plus 0.3, which is 0.5. All right, probability of E and F. Okay, what was E and F? That's going to be, what's in E and in F? E is 2, 3, 5. 1, 3, 5, so it would be just 3 and 5. So what's the probability of E and F? Probability of 3 and 5 would be 0.1 plus 0.3, which is 0.4. All right, so the probability of E given F is the probability of E and F, which we just found to be 0.4, divided by the probability of F, which we found to be 0.5. So that probability would be 4/5. Okay, what is the probability of the pointer landing on a number greater than 4? So we're going to let event G be at number greater than 4, so that would either be 5 or 6. 5 and 6 are the only two outcomes in that event. So what's the probability of event G? Well, 5 and 6, let's see. 5 is 0.3, 6 is 0.2. So what is 0.3 plus 0.2? That probability would be 0.5. Question D, what's the probability of the pointer landing on a number greater than 4, given that it landed on an even number? All right, probability greater than 4 was G, right? Event G was greater than 4, so the probability was 0.5. Given that it landed on an even number, so let's let event H be an even number, which would be 2, 4, 6. What's the probability of that event? 2, 4, and 6. 0.2 plus 0.1 plus 0.2. So I would get 0.5. What's the probability of the pointer landing on a number greater than 4, given that it landed on an even number? So the probability of a number greater than 4, given that it was landed on an even number. So that's going to be the probability of G and H over the probability of H. All right, probability of G and H. We don't have that yet. What is the event G and H? It has to be in G and it has to be in H. The only one I see is the 6. So that's just the event with one outcome of 6. Now, what's the probability of G and H? Okay, the probability of rolling a 6 was 0.2. Okay, so that's 0.2. So this conditional probability would be equal to 0.2 over 0.5. So that probability is 2/5. Example number 5. Suppose that city records produce the following probability data on a driver being in an accident on the last day of a Memorial Day weekend. And they give you this table. Okay, first question says find the probability of an accident. Rain or no rain. So looking at the table, probability of an accident, rain or no rain. So the probability of an accident is equal to the probability of rain accident plus the probability of no rain accident. So I get 0.025 plus 0.015, and that is the number 0.040. And look, the probability of an accident down at the bottom of that column is 0.04. Now find the probability of rain with accident or no accident. So the probability of rain is going to be equal to the probability of rain with accident plus the probability of rain with no accident. So the probability of rain is equal to the probability of rain with accident, 0.025, plus the probability of rain with no accident, 0.335, and that equals the total 0.360. So the probability of rain is 0.360. Now we want to find the probability of an accident and rain. The probability of an accident and rain. So that's going to be, let's see, this gets really fuzzy with notation. I'm going to let that event, I'm wanting to find rain and accident. So that's how the probability of the rain and the accident is this event. And we've already been kind of talking about that. Rain, accident, rain and the accident was here at 0.025. All right, now find the probability of an accident given that it rained. So we're wanting the probability of an accident given rain. That's going to be the probability of an accident and rain, which we just found, over the probability of rain. So we just found that one was 0.025. And the probability of rain was 0.360. So that probability is 0.069. Let's go do one like that again. City records produce the following probability data on a driver being in an accident on the last day of Memorial Day weekend. Find the probabilities. The probability of no rain. Okay, we want the probability of no rain. Here's no rain. The probability of no rain is 0.640. Because you could have the probability of an accident with no rain plus the probability of no accident with no rain. So that probability of no rain is 0.640. Find the probability of an accident and no rain. So the probability of an accident and no rain. Okay, where is that? Probability of an accident and no rain is 0.015. Now find the probability of an accident given no rain. Probability of an accident given no rain. Is the probability of accident and no rain over probability of no rain. We found that to be 0.015, and the probability of no rain was 0.640. So that answer is 0.023. Now let's go talk about intersection of events product rule. We have a theorem that says for events A and B with non-zero probabilities in a sample space S, the probability of A and B can be found two ways. The probability of A times the probability of B given A, or you can say it's the probability of B times the probability of A given B. Either of those two values can be used to find the probability of A and B. So let's go look at an example. If 60% of a department store's customers are female and 75% of the female customers have credit cards at the store, what is the probability that a customer selected at random is a female and has a store credit card? All right, let's go set this up. So our sample space is going to be all the store customers. We're going to let event F be the event that contains all the female customers. And let C be the event that the customers with a store credit card. Okay, it gave us some information. What did it give us? 60% of a department store's customers are female. So we know the probability of F is 0.60. All right, 75% of the female customers have credit cards. So we know the probability of those that have a credit card, given that they're female, right? 75% of the female have credit cards. So probability of having a credit card, given you're a female, is 0.75. So we're wanting to know what is the probability that a customer selected at random is a female and has a credit card. So we're wanting the probability of female and credit card. We can write that as the probability of F times the probability of C given F, because that's by definition. Probability of F times the probability of C given F. So that was 0.60 times 0.75, which gives me 0.45. So the probability of the customer being female and having a credit card is 0.45. Similar question, number 8. If 60% of a department store's customers are female and 80% of the male customers have store credit cards, what's the probability that the customer selected at random is male and has a credit card? So here we go. S was all customers. We're going to let M be that the customer is male. And C be the event that the customer has a credit card. Okay, so what do we know? 60% are female. All right, so if 60% are female, what's the probability of being a male? That would be 0.40, right? 80% of the male have store credit cards. So we know the probability of having a credit card given that you're a male is 0.80. So it wants to know what's the probability that it's male and has a credit card. Probability of male and credit card is equal to the probability of a male times the probability of credit card given male. So that's going to be 0.4 times 0.8, which is 0.32. If you want to see 0.40 times 0.80, it's 0.32. Now let's go talk about probability trees. So the procedure for constructing probability trees is as follows. Step 1, draw a tree diagram corresponding to all combined outcomes of the sequence of experiments. Step 2, assign a probability to each tree branch. This probability is the probability of the occurrence of the event on the right end of the branch, subject to the occurrence of all events on the path leading to the event on the right end of the branch. The probability of the occurrence of a combined outcome that corresponds to a path through the tree is the product of all branch probabilities on the path. And I'll show you what that means in a second. Step 3, use the results in step 1 and 2 to answer various questions related to the sequence of experiments as a whole. So let's look at some examples. Number 9, 2 balls are drawn in succession without replacement. That's important, without replacement. From a box containing 3 blue and 2 white marbles. So if you look over here in the box, we have 3 blue and 2 white marbles. Figure 5 shows a tree diagram for this example. So you're going to start here. You can either draw a white one on your first draw or a blue one on your first draw. And then if you draw a second one, you can either draw a white one on your second or a blue one on your second. So if you drew a white one first, you can either do white 1, white 2, or white 1, blue 2. Or you could draw a blue one on your first one and then draw blue 1, white 2, or blue 1, blue 2. So now we need to assign some probabilities to that. Okay, there were 3 blue and 2 white. So here in the beginning, the probability of drawing a white would be 2 out of 5. The probability of drawing a blue one would be 3 out of 5. All right, let's assume that we drew a white one. So this one is now gone. And we're right here. What's the probability of drawing a white one on your second? Well, that would be 1 out of 4. What's the probability of drawing a blue one on the second? Would be 3 out of 4. Okay. Now let's assume that we drew a blue one on our first. So now this one's gone. The probability of drawing a white on the second would be 2 out of 4. And the probability of drawing a blue on the second would also be 2 out of 4. All right, so now we have all of our probabilities assigned on our tree. What is the probability of drawing 2 white balls? So that's going to be the probability of white on the first and white on the second. That's going to be equal to the probability of white on the first times the probability of white on the second given white on the first. I just think of it this way. I'm going to do 2/5 because I'm going, watch the path that I'm going. I'm going that path. I'm going to do 2/5 times 1/4, which is equal to 2 out of 20. You could write 1 out of 10 if you wanted to. So just follow the path. Our second part of that question, what is the probability of drawing a white ball on the second draw? So getting a white ball on the second draw, there's two paths. I can do white 1, white 2, or I can do blue 1, white 2. So this is going to be the probability of white on the second. That's going to be the probability of white on the first and white on the second, plus the probability of blue on the first and white on the second. We already found white on the first and white on the second. That was what, 2/5 times 1/4? Now, blue on the first, white on the second is going to be 3/5 times 2/4. So that's going to be 2/20 plus 6/20, which is 8/20. Number 10, 2 balls are drawn in succession without replacement from a box containing 4 black and 2 white. What is the probability of drawing a black ball on the second draw? Okay, again, we've got without replacement. So once you pick it, it's gone. The probability of drawing a white on the first is 2 out of 6. And the probability of drawing a black on the first would be 4 out of 6. Okay, let's assume you drew a white one. That's gone. Actually, I could just go like that. Okay, what's the probability of drawing a white on the second? That would be 1 out of 5. And the probability of drawing a black out of the second would be 4 out of 5. Okay, now let's assume that you drew a black one on your first. The probability of drawing a white on the second would be 2 out of 5. And the probability of drawing a black on the second would be 3 out of 5. It's asking, what's the probability of drawing a black ball on the second draw? So the probability of black on the second is the probability of white on the first and black on the second, plus the probability of black on the first and black on the second. Okay, this path, white on the first, black on the second, I get 2/6 times 4/5 plus black on the first, black on the second would be 4/6 times 3/5. So I get 8 out of 30 plus 12 out of 30, which is 20 out of 30. Another example. An auto company A subtracts the manufacturing of its onboard computers to 2 companies, 40% to company B and 60% to company C. Company B, in turn, subtracts 70% of the orders it receives from company A to company D and the remaining 30% to company E, both subsidiaries of company B. When the onboard computers are completed by companies D, E, and C, they are shipped to company A to be used in various car models. Oh boy, this is confusing. It has been found that 1.5%, 1%, and 0.5% of the boards from D, E, and C respectively proved defective during the 3-year warranty period after a car is first sold. What is the probability that a given onboard computer will be defective during the 3-year warranty period? All right, so here's our probability tree. It said, let's get it small so we can see it. Company A subcontracts manufacturing of its onboard computers to two companies, Company B, Company C. So A subcontracts to B, C. It says 40% to B, 60% to C. So this is 0.4. This is 0.6. All right, we got that. Company B, in turn, subcontracts to D. 70% of the orders it receives from A to Company D and 30% to Company E. So 70% to D, 30% to E. All right, that's that paragraph. When the onboard computers are completed by D, E, and C, so they're completed from D, E, and C, and they're shipped to Company A to be used, it's found 1.5%, 1%, 0.5% of the boards, D, E, and C respectively, proved defective. All right, so D, the defective was 1.5. So that's going to be 0.015. That's 1.5%. 1% from E, right? 1% from E is going to be 0.01. And then 0.5% for C, 0.5% is 0.005. Okay, to get this one, we're going to do 1 minus 0.015, so that's 0.985. To get this one, we do 1 minus 0.01, so this is 0.99. And this one is 1 minus 0.005, which is 0.995. All right, what is the probability that a given onboard computer will be defective? So here we go. Probability that it will be defective. We can go that route, which would be 0.4 times 0.7 times 0.015. We can go this route. We can go this route, which is 0.4 times 0.3 times 0.01. And one last route, we could go that route. So that's 0.6 times 0.005. When you do that arithmetic, you will get 0.0084.